Upward and onward with irreducible factors. To show what an irreducible factor is, we're going to factor the bottom and first. We always have to do this. So let's draw a line here. This is actually grouping. And I know that because grouping problems are often grouped into 4 terms. But anyway, we take out an x squared here, and we have an x minus 1 left over. Here we don't really have a GCF except for 1, and x minus 1 is still there. So this is going to be x squared plus 1 and x minus 1. Alright, so you look at this, and you think it kind of looks like a difference of squares, but it's not a difference. And so if you want to factor that, you actually have to use complex numbers. And so when we don't go into that world, we call it just irreducible, or prime. So what this means is that x minus 1 is still going to be one of our denominators. But this will be a denominator, and there's something special about this denominator. It's a power of 2. And so we have to have a possible answer of 1 degree less. So since it's a power of 2, 1 degree less would be a linear possibility. And so, for example, if we had like x cubed plus 1, we would need to then put, for example, bx squared plus cx plus d upstairs because the power is 3. The thing on top is always going to have a degree less. So yes, if you had a 10th power plus 1, it's not reducible, and so we would have to put a 9th power on top. But that's not really going to happen. This right here is how we would set it up with this irreducible factor. Okay, but we do everything else the same, so it's x squared plus 1. And I'm just finding common denominators again. Alright, and this will be equal to ax squared plus a. I'm just distributing the a in. But this right here will have to be FOILed with x minus 1. So bx squared plus negative bx plus cx minus c. Alright, now let's highlight our squareds. Those will all go together in the system. So we'll have a plus b equals 1. Let's look at our x's. Alright, so we have negative b plus c equals 4. And finally, we have a, negative c, and 1. So a, negative c equals 1. Alright, now to solve this, I'm going to use elimination. And what I notice is that these two, if you were to add down, like if I put a sum bar right below and did this, the b's would cancel, and I would get a plus c equals 5. I still have this other one, though, that I haven't used yet. That's part of my system. Okay? Now, if I add down, look at that. The c's cancel. I have 2a equals 6. So I know right away a is 3. Now I could plug it in anywhere else I want. So to get c, I could plug it in here. It'd be 3 plus c equals 5. C is equal to, well, take away 3 and you get 2. And then to figure out b, I could plug a in right here. So this would be 3 plus b equals 1. So b has to be negative 2. Alright, so what does this mean? This means I'm going to have 3 over x minus 1. Then we're going to add a negative 2x plus 2 as c all over x squared plus 1. The nice thing about these, again, is if you need to check your work, you can go to Wolfram Alpha, and if you plug in this right here and write decompose, it'll do the answer for you. Or if you write this in and ask to combine it, it will combine and return back to what we started with. So give this a shot. Here is a try problem. Remember, you got to factor the denominator first to figure out what your possible denominators will be in your partial fractions. Okay, so factoring this out, we get a GCF of x. It's x squared plus x plus 5. What I notice here is that this is not factorable. So this means that I'm going to have an a over x, and this is my denominator. But again, because this has a degree of 2, I'm going to include a bx plus c here, because it'll be a degree less. Alright, and then basically you'll notice that we cross multiply here. So a is going to be multiplied by x squared plus x plus 5, and then this whole thing will be multiplied by x. It's not really cross multiplication, but you'll notice you always do this to find common denominators. So I have 8x squared plus x plus 15 on my left, and on the right and then this will be plus bx squared plus cx. Alright, highlight our x squareds. What I get is a plus b should equal 8. Then, how about my plain x's? Yep, so we should have a plus c equals 1. And what's left over? 5a equals 15. Well, this is really nice because a is 3. Plug this in here. 3 plus what is 8? That means b is 5. And then you can plug it in even here. So 3 plus what will give me 1? C is negative 2. My answer. That should be a 5x minus 2 all over this. Okay, so we're going to look at just one more ugly setup here. For example, what if you encounter 2x cubed minus x squared plus 5x, and that is all over this? Well, we have two things going on. We have an irreducible, but remember the rule for multiplicities. This means we have to have a denominator of x squared plus 1 and x squared plus 1 squared. And think about this. We're going to have ax plus b right here and cx plus d. And so you're going to be dealing with not only irreducibles, but higher powers because they are squares. You're going to have linears on top. So let's get into this. If you were to write this out as x squared plus 1, maybe it's easier to think about common denominators. So basically, we're only going to multiply this side by x squared plus 1. The other side then would have the same denominators. We don't have to multiply cx plus d times anything. So it's going to be 2x cubed minus x squared plus 5x. And I got to FOIL this out. Ax cubed plus ax, and then we have cx plus d. Now the system we make here is kind of funny because it's going to be pretty simple. A is 2. B is going to be negative 1. C and A together are going to be 5. So this one, and this one. And then B plus D should equal 0. Alright, so if I plug my A in here, I know that C has to be 3. And if I plug my B in here, I'm going to have that D equals 1. So that system actually was really pretty easy. The setup's ugly, but it's really not that bad. So this is going to be 2x minus 1. And then we'll have 3x plus 1 over the double irreducible. And here we go.